In this video, we'll be seeing about the analysis of an asynchronous sequential circuit, stable and unstable states, races, and cycle. We know that in asynchronous sequential circuit, we don't have a clock, and therefore the internal state will change when the input changes. So here we have the block diagram. So we have the inputs, the outputs, and then we have the feedback loops. The values here will be denoted by capital Y. These are the next state variables or the excitation variables. So these excitation variables are fed to the circuit through these delay elements. The values after these delay elements, the values here will be denoted by small y. They are called as the secondary or internal variables or the present state variables. So due to these uneven delays, we don't know the order in which these variables will change. So we will encounter a timing problem. So this problem will not be there in synchronous circuit which is edge triggered, because the circuit is allowed to change only during this short time of pulse transition. So to ensure a proper operation, we assume the fundamental mode. So in this, only one input can change, and only after the circuit has attained a stable state. The circuit will be stable when the current state is equal to the next state. Let's quickly take an example. So here we have a gate type asynchronous circuit. It has a single input X and two feedback loops. So in a combinational circuit, I don't have to introduce any external delay elements because I know that the gates and the wires have their own internal delays. So the propagation delay for the signal to travel from Y from the current state to the next state will be the delay of this circuit. So for the first step in analysis is to identify the feedback paths, and then I derive the Boolean expression for the excitation variables in terms of the input and the current state. So y1 will be x and y1 or x bar and y2. And similarly I obtain for y2, and then I expand y1 to standard form. And then I map these to a slightly different K-map where the rows will be the present state and the columns will be the input. And similarly I obtain for y2. And then to obtain the transition table, I have to combine these two tables 0, 0, 0, 0, 0, 1, 0, 1. And I similarly fill all these cells. So the value in this cell will be the next state. It's a next state variable, right? So this is y equal to y1, y2. And I know that for a circuit to be stable, the current state should be equal to the next state. So 0, 0 is equal to 0, 0. Current state is equal to the next state. Therefore, this is a stable state. I circle it. 0, 1, 0, 1, stable state. 1, 1, 1, 1, 1, 0, 1, 0. So this is how we obtain the transition table. If I label these states with alphabets, I get the flow table. So I replace this table with alphabets instead of the states. I get the flow table. So this is a primitive flow table because it has only one stable state in each row. And a total state will be when you combine the current state and the inputs. So a total state of this circuit, the circuit has 4 stable total state, which is 0, 0, 0, 0, 1, 1, 1, 1, 0 and 1, 0, 1. The next topic will be races. So in the previous circuit, we can see when the input changes from 0 to 1, only one of these state variables change. 0, 0 to 0, 1. Only y2 changes. But here, when the input changes from 0 to 1, both of these binary state variables change simultaneously. 0, 0 to 1, 1. And we will encounter a problem here because we have uneven delays in the feedback path. We don't know which value will be reflected here first. So let's say the circuit is in the total stable state 0 0 0 and the input changes from 0 to 1. So the next state will be 1 1. Due to the uneven delays, the current state can become 0 1 first, or 1 0, or 1 1. So if the current state becomes 1 0 1, the next state will be 1 1. If it's 1 1, the next state will be 1 1. And if it's 1 0, the next state will be 1 1. And we can see for the current state 1 1, it is a stable state. Therefore, irrespective of the order in which the variables changes, the circuit ultimately attains a stable state. Therefore, it is a non-critical race. But here, say it transitions from the state 0 0 to 0 1 first, it will attain a final stable state of 0 1. If it goes to 1 1, it will be the state will be 1 1. If it goes to 1 0, the final state will be 1 0. So here the final stable state completely depends on the order in which the variables change. So this is a critical race. One of the ways to avoid races will be cycles. So in cycles, we direct the circuit through a unique sequence of unstable states. So here, when the input changes from 0 to 1, the state changes, the next state becomes 1 0 1, and that would become the current state. So 0 1 will become 1 1, 1 1 will become 1 0, and 1 0 will become 1 0, which is a stable state. So the circuit will attain a stable state. So we have to make sure that the cycle terminates with a stable state. If it doesn't, it will keep oscillating between these unstable states. So here it goes from 0 1, the current state will become 0 1, it will give 1 1, 1 1 will give 1 0, 1 0, it will keep oscillating between these unstable states. That's it for this video. Thank you for watching.